Welcome back to my channel Nature of Physics and Art and part 4 video from the electric dipole, that is here time period of oscillation of electric dipole in a electric field, and also we can find the frequency of the electric dipole. Okay, think practically here. This is the electric dipole, this is the negative charge, this is the positive charge, O is the center. Okay, it is doing simple harmonic motion, that is like this. From the this is in the direction of electric field, that we can take stable equilibrium position. From stable equilibrium position to it gets small angular displacement like this, small angular displacement. So for example like this. Okay, here plus q charge, here minus q charge, it is making an angle theta with the stable equilibrium position. Okay, so think practically. Already we know very well torque acting on a dipole. So torque, okay, which is equal to P into E sine theta. Okay, so next on the electric dipole, what happened? The dipole which is turned to rotate in the direction of electric field, and finally what happened? It do small oscillations with respect to mean position and finally comes to rest position. Because of always electric dipole is stable equilibrium in the direction of electric field. At certain position I am taking theta. Okay, so what is acting here? Restoring torque is acting on the electric dipole to turn the dipole in the direction of electric field. So this is taken as deflection torque. So this is deflection torque. Okay, and next one is a restoring torque. So restoring torque. Okay, this is deflection torque is D, restoring torque is tau R, which is equal to I into alpha. I is the moment of inertia of the electric dipole and alpha is the angular acceleration. I, moment of inertia, and okay, alpha angular acceleration, acceleration. See, because of angular displacement, rate of change of angular displacement, angular velocity, rate of change of angular velocity is angular acceleration. See, think practically. So this is taken as equation number 1 and this is taken as equation number 2. So deflection torque or restoring torque, which is equal to deflection torque, both are equal in magnitude, opposite in direction. Deflection torque and restoring torque both are equal in magnitude, opposite in direction. This is the deflection torque, this is the restoring torque. Restoring torque is developed in the electric dipole that try to rotate in the direction of stable equilibrium position of the electric dipole in the direction of electric field. Okay, so for this the values are replacing here, that is I alpha, which is equal to, okay, minus PE into sine theta. Okay, sine theta for small angles, okay, sine theta is approximately equal to theta. So then I alpha, which is equal to minus PE into theta. So alpha, which is equal to minus PE divided by I into theta. Okay, from simple harmonic motion, so that alpha, which is equal to minus omega square into theta. See, comparing the both equation, alpha is the angular acceleration, minus is there, theta is there, and instead of omega square we have to write here omega square, which is equal to, that is PE divided by I. Okay, so we can find the omega. Based on the omega we can find the time period and frequency. Just a second, I will clean the board. See, already we got omega square is equal to Pe divided by I, where P is the dipole moment of electric dipole, E is the electric field intensity, and that is uniform electric field we can take, and I is the moment of inertia of the electric dipole. So from this equation here, omega, which is equal to root over Pe divided by I, okay, and omega value is 2 pi by T, so which is equal to root over Pe by I, and okay, this is taken as equation number 1, and time period T, which is equal to 2 pi, okay, so 2 pi root over I divided by P into P. This is taken as time period, second equation. And frequency, next one is frequency, okay, frequency mu, which is inversely proportional to the time period. So frequency mu, which is equal to 1 by 2 pi root over Pe divided by I, okay, this is taken as equation number 3. So equation 2 represent the time period, so that time, okay, so that time period, 1 minute. Okay, sorry for the mistake. Okay, this is completely time period and frequency of the electric dipole. Thank you. Okay, this is part 4 video is completed. Now continuation, next part 5 video, that we will discuss potential introduction and EVD relation. Then we can discuss in the next video from the potential of the electric dipole, then relations electric field intensity on the axial line and equatorial line based on the radial electric field and tangential electric field. Very interesting topics those are. Okay, thank you and bye. See you later.